Ever since man invented the wheel, he has been trying to find a better way to stop it from turning. Braking systems became more complicated as weight on the wheel and speed of rotation increased. Today's train brake systems are very complex and require skilled employees in maintenance and operation. But to learn these skills, it's necessary to first understand the fundamentals of the system. Let's begin with the final result, the action that causes the wheel to slow down or stop. The most common method is to force a brake shoe against the rotating wheel at varying pressures. During pioneer days, brakes were operated manually by a simple lever. When force was exerted at the top of the lever, the shoe at the bottom was pressed against the wheel. Notice that moving the fulcrum point or changing the length of either end of the lever affects the pressure on the wheel. In the early days of railroading, train brakes were applied by hand. When the engineer wished to slow the train, he blew a signal with the engine whistle. The brakeman, hearing this signal, would go from car to car, over the top, applying hand brakes. Another whistle signal told them to release the brakes. In the late 1860s, George Westinghouse devised a way of forcing the brake shoe against a wheel by using air pressure. The air pressure acted against a piston that moved inside a cylinder. The piston movement was then transmitted through a rod and levers to the brake shoe. George found that he could increase the brake force not only by levers, but also by increasing the piston area. If he doubled or tripled the area of a piston, he could double or triple the force on the brake shoe. This is caused by the fact that air pressure is exerted equally against every square inch of the piston surface. Increasing the number of square inches will increase the total force. We always state the amount of pressure in pounds per square inch, or PSI, instead of trying to determine the total force. George Westinghouse used these principles to build a train air brake system. He installed a steam-driven air compressor on a steam locomotive and connected it to a large tank or reservoir which held a supply of compressed air. He then connected the reservoir to a valve located at the engineer's position. When the engineer wanted to slow the train, he would pull back on the valve handle. This would allow air pressure to flow from the reservoir into a brake pipe. The brake pipe was connected to each car in the train through cocks, flexible hoses, and couplings. A branch pipe connected the brake pipe to a cylinder on each car. When the engineer felt the braking force was sufficient, he would move the handle forward until the valve was closed or lapped. This held air pressure in the cylinders and kept the brake shoes against the wheels. To release the brakes, he pushed the valve handle all the way forward. This opened the brake pipe so that pressure could escape from the system. When the air pressure was released from the cylinders, a light spring would push the pistons back, pulling the brake shoes away from the wheels. This system proved to be a big improvement over the use of hand brakes. However, it wasn't long before a train separated. An air hose burst, or maybe the brake pipe was broken. Guess what happened then? No brakes. Undaunted, George went back to the drawing board. In the early 1870s, he came up with a fail-safe system. By reversing the direction of airflow in the brake pipe, the brakes would apply automatically if the pressure should escape. This meant putting pressure into the brake pipe to release the brakes and taking pressure out of the brake pipe to apply the brakes. In order for this system to work, George had to provide each car with its own supply of air pressure. So he placed a separate reservoir on each car, which was auxiliary to the reservoir on the locomotive. Then he designed a valve for the car, which would control the charging of the reservoir, applying the brakes and releasing the brakes. The valve was the heart of the car brake system. On command from the brake pipe, it would perform these three distinct functions: charge, apply, and release. Because of this triple duty, the valve became known as a triple valve. If we learn how the triple valve works, it will reveal the basic operation of today's complex control valves. Although many additions and refinements have been made, the principle remains the same. This knowledge can be helpful in avoiding pitfalls and solving many air brake problems. The early triple valve was made up of a piston that moved back and forth in a cylinder. The piston had a stem attached to one side that moved a brass block, called a slide valve. As the slide valve was moved, it opened or closed connections to control airflow. The chamber to the left of the piston is connected to the brake pipe. As pressure enters from the brake pipe, the piston is pushed to the right, moving the slide valve. When the piston is pushed to the right as far as it will go, a small passage called a charging port is uncovered above the piston. Air pressure from the brake pipe can squeeze through the charging port to the other side. The pressure then begins to build up slowly around the slide valve and up into the auxiliary reservoir. Air pressure will continue to flow through the charging port as long as brake pipe pressure is higher than pressure on the other side. Because of the small opening, it will take about 7 or 8 minutes to build up to that in the brake pipe. When pressures are equal, the system is fully charged. Let's charge this system to 80 pounds. If we maintain 80 pounds pressure in the brake pipe, it will slowly build up to 80 pounds around the slide valve and in the auxiliary reservoir. Now we can apply the brake by reducing pressure in the brake pipe. Suppose that we reduce brake pipe pressure 10 pounds, from 80 to 70. As pressure begins to drop on the brake pipe side, the piston will start moving to the left. This movement is caused by higher pressure pushing against the right side. The charging port is so small that pressure cannot flow back through it as fast as brake pipe pressure is being reduced. And the first movement will close off the port. As the piston moves further, the slide valve is pulled along to close the exhaust opening from the brake cylinder, shown by the arrow. With reduced brake pipe pressure, the piston continues to move all the way to the left. In this position, the hole drilled through the slide valve will line up with the pipe connected to the brake cylinder. Now, air pressure from the reservoir and around the slide valve can flow down to the brake cylinder to apply the brake. As air pressure flows from the auxiliary reservoir to the brake cylinder, reservoir pressure is reducing. This flow will continue until the reservoir pressure is slightly below the 70 pounds remaining in the brake pipe. When the reservoir pressure is slightly lower than brake pipe, the piston will move toward the lower pressure, or toward the right. This movement continues until the slide valve is moved far enough to close the opening to the brake cylinder. When all ports are closed, the valve is said to be lapped, and the brakes will be held applied. If we wish to apply the brake harder, we can make a further reduction in brake pipe pressure. Each reduction causes the piston and slide valve to move, opening the port to allow more reservoir pressure to flow to the brake cylinder. In this way, we can apply the brake in small steps or graduations. To release the brake, we must increase brake pipe pressure. When the pressure on the brake pipe side of the piston becomes greater than that remaining on the reservoir side, the piston and slide valve will move toward the right. Now, all air pressure in the brake cylinder will exhaust through the slide valve, and the return spring will return the brake cylinder piston to release. One thing you should note here, once the valve moves to release, all brake cylinder pressure will be released. The brake cannot be released in steps or graduations. Another important fact to remember, that brake pipe pressure will increase quite rapidly, but auxiliary reservoir pressure will increase very slowly. Here we see that brake pipe pressure already has reached 80 pounds, but reservoir pressure has only recharged to about 70 pounds. If it were necessary to apply the brake again at this point, we would get no brake cylinder pressure until after brake pipe was reduced more than 10 pounds. This is the fundamental principle of train air brakes. The brakes will release when brake pipe pressure is above auxiliary reservoir pressure. The brakes will apply when brake pipe pressure is below auxiliary reservoir pressure. This principle can help you to understand and to solve many air brake problems. There are two methods by which the valve can be moved to release position. Either increase brake pipe pressure or reduce auxiliary reservoir pressure. All control valves are now equipped with a reservoir release valve. By pulling part way out on the rod, reservoir pressure will be reduced and the brake will release. Up to this point, we have not discussed the pressure developed in the brake cylinder when the brake is applied. To understand this, we must first learn a few facts about the brake cylinder. When there is no air pressure in the cylinder, the piston and rod are held to the right by a light spring called a return spring. The action of the return spring pulls the brake shoes away from the wheels when the brake is released. When the brake is applied, air pressure enters the cylinder and soon overcomes the spring. The piston and rod move toward the left until all brake shoes are up tight against the wheels. The length of movement will depend on brake shoe wear and condition of the levers and pins. Brake cylinders are given a nominal piston travel. That is, the point where the piston should be when the brake is fully applied. This point determines the space or volume that must be filled with air pressure. If the piston travel is longer than nominal, the volume will be larger. If the piston travel is shorter, the volume will be smaller. When the piston is at its nominal travel, the volume in the auxiliary reservoir is just 2½ times larger than the volume in the brake cylinder. This 2½ to 1 ratio can be used to determine the brake cylinder pressure. We found earlier that for each pound of brake pipe reduction, a pound of pressure would flow from the auxiliary reservoir to the cylinder. Now, we shall see that each pound of pressure from the reservoir becomes 2½ pounds in the brake cylinder. This can be seen more clearly by using two water tanks. The larger tank represents the auxiliary reservoir. The smaller tank represents the brake cylinder. Each is 80 inches high. Now, suppose we connect the two tanks at the bottom through a valve, and the valve is closed. Let's begin with the large tank filled to the top, indicating that the reservoir is fully charged. The small tank is empty, indicating that the brake is released. If we open the valve between the tanks, water will flow from the large tank to the small tank. As the water level drops down in the large tank, it comes up in the small tank. Let's close the valve when the water level has dropped 10 inches in the reservoir. Now we can see it has risen 25 inches in the cylinder because of the 2 1/2 to 1 difference in volume. Each time we open the valve, water level drops in the reservoir and rises in the cylinder. There will be 2 1/2 inches added to the cylinder for each inch of drop in the reservoir. Here we see that the reservoir has fallen to 60 inches and the cylinder has risen to 50 inches. This brings us to another important fact. What would happen if the valve were left open? When the reservoir drops to about 57 inches, the cylinder will increase to about 57 and the levels will be equal. No more water will flow between the tanks. This point is called equalization. Equalization is the point at which reservoir and cylinder are at the same level. In air brakes, equalization is the highest amount of braking that can be obtained during a normal application. This is true because only one reservoir, the auxiliary reservoir, is used normally. To get stopped quicker in an emergency, a second reservoir had to be added to each car. The second reservoir, called an emergency reservoir, is charged in the same manner and to the same pressure. However, it is not used during normal braking. When an emergency stop is required, both reservoirs, auxiliary and emergency, are equalized with the brake cylinder, providing a 20% increase in brake cylinder pressure. The control valve must now be able to recognize a normal application from an emergency application. Since the pressure must be reduced in the brake pipe to cause an application, somehow the reduction will have to signal for either a normal or emergency application. The solution was to devise an additional valve that would respond only when emergency applications were needed. Normally, the engineer exhausts air pressure from the brake pipe slowly. But in an emergency, he exhausts the pressure rapidly. The valve designed to make this distinction was called a quick action valve. Its operation depended on air pressure flowing through a small hole or choke, shown here in the piston. The quick action valve is charged similar to the triple valve. But when brake pipe pressure is reduced at a normal rate, the pressure flows right back through the hole, and the piston does not move. However, if the brake pipe pressure is reduced rapidly, pressure cannot get through the hole as quickly as the brake pipe is reducing, and the piston will be moved to the left. The piston movement will cause several things to happen. First, it will open a vent valve to dump all air pressure out of the brake pipe. Second, it will connect the emergency reservoir to the auxiliary and brake cylinder, raising cylinder pressure about 20%. If the small choke becomes clogged, air pressure cannot reduce in the chamber at the same rate as brake pipe. This can cause brakes to apply in an emergency when a normal or service reduction is made. This condition is often referred to as a kicker or dynamiter. Remember, it's not the amount of air taken out of the brake pipe that triggers an emergency. It's the rate at which air pressure is reduced. That's why train brakes can be put into emergency when opening an angle cock too quickly. After an emergency application, the brake pipe cannot be recharged, nor can the brakes be released until all vent valves have closed. This usually takes about 90 seconds. Modern control valves, now called AB valves, have many improvements over the old triple valves. The service and emergency portions have been separated to improve stability. Features have been added to transmit both application and release of brakes more rapidly throughout the train. One such feature is called quick service. The quick service feature makes a small reduction in brake pipe pressure at each control valve when a service application is first started. It helps to transmit or propagate the application throughout a long train. And it ensures that each car in turn will have the brakes applied once an application is started. Improvements were made in the original AB valves, and they became ABD valves. A feature added to the ABD valve is the accelerated service release. This feature causes a faster release of service applications by allowing the unused emergency reservoir pressure to help build up brake pipe pressure. Now, when brake pipe pressure is increased only a pound or so on the first car, the valve will assist in building up brake pipe pressure so that the next car will release and each car in turn adds air to the brake pipe. This feature has caused the brakes to release on a few standing drafts of cars, resulting in runaways. To avoid such consequences, it is important that the brake pipe be completely depleted and an angle cock be left open on any drafts that are not attached to a locomotive. If this is not done, the cars should be secured with hand brakes. The most recent control valve is called an ABDW. This valve has an accelerated service feature, which causes service applications to travel faster throughout the train. It is similar to the quick service feature, but acts continuously whenever brake pipe pressure is being reduced. The presence of ABDW valves in a train will cause a shorter brake pipe exhaust when making service reductions. An engineer can easily mistake this for a closed angle cock or an obstruction in the brake pipe. Now let's look at some of the problems that can occur with car brakes. We said at the beginning that the purpose of a brake system was to force the shoes against the wheels. That's how we must determine if a brake is working or not, by checking to see if the shoes are against or away from the wheels. Brake failures can be easily classified into two categories. Either they fail to apply or they fail to release. If the brake fails to apply, check the brake cylinder first. If the piston is extended out, the problem is in the rods and levers or the brake rigging. They may be bent, broken, disconnected, or fouling. If the piston is not out, the problem is in the air system. Make sure the reservoirs have had time to charge sufficiently. Remember, the air must first be stored in the reservoirs before it can enter the cylinder. And remember also that brake pipe pressure must be reduced below that in the auxiliary reservoir before the valve will move to apply the brake. If the reservoir has not been allowed to charge sufficiently, don't keep trying to apply the brake. Wait a reasonable time for charging. The reservoirs are charged only while the brake is in release. A quick way to tell if the reservoirs are charged is to give a tug on the reservoir bleed rod. If a strong blast of air pressure is obtained, the reservoirs are charged. If it's only a weak blast, they are not charged enough. If it appears that the reservoirs are not being charged, check to see that there is air pressure in the brake pipe. Check that all hoses are coupled between cars and the angle cocks open. Be sure there are no obstructions in the hoses, such as kinks, dirt, ice, and so forth. And check the angle cock on the end of the draft or train to see that it's closed. Check the cutout cock in the branch pipe just ahead of the control valve. It must be open. This cock works opposite to the angle cocks. When the handle is in line with the pipe, the cock is closed. The handle should be at a right angle or crosswise to the pipe to be open. If the brake is applied but fails to release, check the handbrake first. After releasing a handbrake, always check the shoes to see that they are away from the wheels. The chain may be caught or the rigging fouled. If the retainer valve handle is turned up, the brake will not release. Make sure the handle is in direct exhaust position, pointed straight down. Another problem that frequently prevents a brake from releasing is an overcharged reservoir. This can easily be corrected by releasing some pressure from the reservoirs with the bleed rod. Pull the rod out fully to release air from both reservoirs. If this succeeds in releasing the brake, make another application and release to be sure that it was just an overcharge. There are many problems like these that can be corrected easily, on the spot, without tools. But it requires a basic knowledge of how the air brake system works. Although it cannot be seen, there is nothing mysterious about it. The secret is simple. Diaphragms or pistons move because the pressure on one side is higher than the pressure on the other side.